So it's a pleasure to have Dr. Ana Larrañaga Janeiro here from University of Vigo. We've been working together for a couple of years now on shape optimization and kind of machine learning applications during her PhD, which you finished earlier this year? July, okay. She's been a postdoc at University of Vigo for a few months, and we have extended an offer for her to come to University of Washington. So hopefully she joins us in a few months, and maybe many of you have had a chance to meet her already. So it's really a pleasure to have you here to tell us about your work on learning the shape. Thank you.
Okay, so thank you, Steve, and thank you everyone for coming. So as Steve mentioned, we've been working for kind of a long time on shape optimization problems in general. And today I'm going to dive a little deeper into what's about this shape optimization, complex shapes, irregular parameterization, which is a challenge that everyone faces in industry nowadays. So to start with, okay. So many of you might be thinking, what's this and why I'm showing you a picture of sea lions, right? And what does this have to do with today's talks? Well, quite a lot. Sea lions have a really good way of heat regulation, thermoregulation, by using their fins when they're really hot. And that's something that we use in engineering nowadays as well. When you have a plane surface, usually you want to add fins to increase the heat surface area in order to increase the efficiency of this microsurface or surface that they have fins in heat exchangers. And this is a sample in nature where it's an animal that has fins with the same purpose as we have nowadays. Now, this has a lot to do with today's talk because it's going to be all about heat transfer and heat transfer optimization for heat exchangers. Now, when you're trying to optimize a microsurface texture or any texture that it's used for heat transfer, you don't only have to focus on fins, but also on pressure drop. This is a sample of a shark's skin. Maybe somebody of you have seen it before, but basically they have these really cool textures around their skin that helps the flows around the skin of the shark to be, let's say, better, so they can swim better around the ocean. This has to do a lot with heat efficiency regarding fins, because when you are trying to optimize heat transfer for microfins or fins in general for heat transfer, you both have to increase the heat transfer from the surface, but trying to also decrease pressure drop as well. So these are going to be the two main targets that we are going to be focusing on today when we are trying to design new shapes for fins. Now, as I've mentioned, these are just some examples that we have in nature nowadays. So the idea is, or what we thought at the beginning of this project was, why do we have to focus on just such a really irregular straight shapes, so like rectangles, squares, when we are trying to design these surfaces, and why do we don't take some inspiration from nature, basically? So currently, and at the beginning of this research as well, microfin designs and designs in fins in general lack a lot of innovative alternatives. So as I've mentioned, most of the aspects, or let's say alternatives that were published, were regarding regular shapes, mainly because it's different to manufacture any other thing that a rectangular fin. Most of you might know that, but nowadays there's a lot of progress with an additive manufacturing, and that's something that we wanted to use for this project. So the idea is, could we propose any other fin that it's better than what we had nowadays, and use any additive manufacturing tools that we have nowadays in order to manufacture it? So in order to do so, there's a lot of research that has to be carried out before you can manufacture anything. And if you want to run any numerical simulation using microfins, that's a really costly numerical simulation to run, because you have to obey some mesh requirements, and also depending on the turbulence model and so on and so forth that you use, the complexity and the amount of times that you need to basically carry out any optimization tasks can be really costly. So the idea was, can we train any machine learning model to learn from the shape, discover new unseen geometries, and trying to avoid the machine learning task or the data-driven model to focus on really constrained concepts? So the idea was, can we improve the parameterization of the geometry that we start with to find new geometries that haven't been used in industry, and that allows us to construct a data-driven model that could be used for an optimization task? And that's the main motivation for today's talk. So here you have an overview of the main points that I'm going to talk about. First, I'm going to talk very briefly about the complexity of parameterization in irregular contours. Then I'll dive into how we approach this problem from an engineering point of view. So basically what we did was constructing our own database. The motivation behind that is because there was basically no database available open source of microfilms designs available for any data-driven task. Most of the databases that were available at the time were kind of simple, so regular geometries, so on and so forth. Most of them focus on turbulence model, nothing regarding like heat transfer tasks, such as this one. That's why we had to carry out many numerical simulations to build or basically source of knowledge. Then we constructed our surrogate-based optimization. And then at the end, I'm gonna dive a little deeper into these new parameterization techniques that we've been working on for the past few months. So to start with, the complexity of parameterization of irregular contours is not a new topic for any of you, probably. There are many ways that you can use to parameterize any geometry. The most basic one would be Cartesian description. So basically you just take points around the contour and that's your way of discretizing the contour. Now, this works well, it's simple, but if you want to carry out any, as I've mentioned, numerical simulation, make sure that it's stable, so on and so forth, it's very not efficient way to parameterize any geometry because you need a lot of degrees of freedom to do so. So we can do better nowadays. Other alternatives could be, for example, surface triangulated meshes, which are a good alternative. They're very flexible for complex surfaces, but they're really memory intensive. So this could be an option, but still there's a lot of computational resources that we would need to do this. And we have a really, let's say, special way to characterize our microfilms. So this was not a good idea either. And there are also, for example, implicit methods that you could use as well, but these are really well for smooth surfaces, and that's nothing similar than to our films. I will dive deeper afterwards on why don't we have good shapes for our films. But again, this was an alternative, but not really fitted for our purpose. And there are many other ways that you can parameterize a geometry, but the idea is that we needed to find this shape parameterization that could have as few degrees of freedom as possible, but that it could capture all the necessary information for a data-driven to train efficiently, be able not only to interpolate, but also extrapolate, which is a really complex task to do. So up until now, as I've mentioned at the beginning, there are a lot of regular designs that lack the possibility of innovative microframe designs. And what we want to do is to push limits a little forward, find some complex contour. And this is a really tedious task because it's moving inside of high dimensional spaces. So if you move towards more irregular shapes, then it's gonna be more difficult to characterize it. Our main idea that, as I've mentioned, I'm gonna dive deeper at the end of the talk, was using Fourier analysis to parameterize the geometry. Now, this, surprisingly enough for us when we started, has not been used in engineering as much. It has been used for other tasks in the bioengineering, so for some particle sound characterization and so on, but not so much in engineering. So we were curious about that. And basically, we were curious about using this for such a purpose, so like a real application as we have this. So to start with, I'm gonna go really really briefly, into how we generated the database. So to start with, we decided to use a base microfilm shape, a T-shaped microfilm shape, to trying to maximize the available degrees of freedom in our space, also to generate secondary flows, improve turbulence in the intermediate regions of the microfilms. And also we wanted to give as much freedom as possible for the generation of the microfilms. So this, for example, is an example of one microsurface that we have in our database. And as you can see here, we have 15 films. So the idea was to generate one geometry and create a pattern. The reason behind this was to avoid any effect of the entrance flow and also the outlet flow. So we focus on the intermediate region of the microphase surface to measure any effect of heat transfer and so on and so forth. So again, this is an example. And another thing that it's kind of interesting about this database is that we fixed the physical boundary conditions of the numerical space, and we only moved the geometry. So the geometry is the only thing that is changing. Just because it's too complex, if you want to simulate 1,000 different geometries with 1,000 different physical boundary conditions, that's not feasible. So since we were really interested on the contour itself, we chose boundary conditions that are common in industry, and we move forward into the geometric parameterization and the generation of different geometries. So to start with, as I've mentioned, we chose a T-shaped microfin, and for us, the parameterization has 15 parameters, which are the vertices around the fin, and also the separation between contiguous fin. We have 15 microfins in our microtexture surface, so we have the X and Y coordinates as our parameterization, and these 2 points at the base of the fin are fixed to the base, so to avoid the fins flying around, basically. So the idea, in order to have as least human bias in the generation of this geometric parameterization, we follow like a Monte Carlo approach. So we generated a uniform generation of random combination of these 15 numbers to generate thousands and thousands of microfins. Here are some examples. And basically, we just implemented a few requirements that the fins had to have. So for example, you cannot have elements that are really small, sharp edges, so on and so forth. Some of the geometries that are included in our database are really special. So this doesn't mean that you can manufacture the microfins as they are. The whole purpose of this was to propose like a proof of concept case, so learn from it. So as this combination of 15 numbers were generated randomly, we had to implement a feasibility assessment or sanity check after the generation of the geometries was undergo. As I've mentioned, there are thousands and millions of combinations of these 15 numbers that you can do. So basically we just generated a few thousands, and then we made sure that all of the combination of these 15 random numbers follow this sanity check or feasibility assessment that we call. And basically, the idea was to, again, generate the random numbers and then put some restrictions as to how these geometries were generated. Basically, for example, to avoid intersections, sharp edges, basically like that one vertex will not go over one that it's contiguous to it. So a few restrictions regarding how do you generate this geometry. Now, the reason for this is because the running of these numerical simulations to generate our database was automatic. So even though it was run in batches of a few hundreds, there was still a need for it to be kind of autonomous. So basically you generate the combinations of numbers, you make sure that it follows the sanity check, and then you can go ahead and run the numerical simulation because it's supposed to not fail in the middle. So by doing so, we constructed our CFD database. It contains almost 16,000 numerical simulations of microfins, again, with fixed boundary conditions, but they follow some, let's say, numerical simulation requirements to make sure that all of the simulations are converged, that there's no effect of the entrance and outlet flow, and that there's enough space in the channel to avoid any effects of secondary flows around the microsurface texture. So with this, basically, we already constructed our database of knowledge. And the first idea was basically to see what we had. Again, we generated this randomly. So at the beginning, we didn't even know what we had. So this was a very brute force approach at the beginning, probably not the best one to take, but since we were trying to construct something to learn from it, basically. So as I mentioned, if you're trying to optimize the geometry of a microsurface texture, what you have to do is to optimize both the thermal performance and the hydraulic performance of the microsurface texture. So on the one side, we focus on heat flux and also the average temperature and minimum temperature of the intermediate fins in the micro surface texture. And also we measure the pressure drop and several drag coefficients in the domain. Now, as you can see here, this is an overview of the information that we had in our database. And also, as a way of combining the both targets, you can measure, for example, the fin efficiency. Something interesting was that there were a couple of fins that randomly enough, they basically did the opposite of what they were meant to be. So instead of dissipating heat, they were doing the opposite. They weren't dissipating heats. Why? The reason why I'm highlighting this is because there are outliers in our database that at the beginning hampered the learning of the any data-driven model. And this was something to take into consideration further on in the work. So at the beginning, we constructed some Pareto frontiers, just choosing some targets that were used in literature. So for example, here you have a plot that has the pressure drop versus the efficiency, which are again, the two main targets that we want to focus on. And it's interesting to say that even though these geometries were generated randomly, they have physical sense. So for example, this one on the top, the number 0, is one that has a higher efficiency. This makes sense. Higher efficiency means higher heat flux, and that's because it has a wider base. So yet it allows higher heat flux through the fin. Now, for example, in the other side, you have some examples of fins that don't have as much pressure drop, and that can be also because of the inclination of the fin. So if it has an arrow shape, if it's pointed towards one side or the other. So this is important to do, and it was important for us to do just to make sure that the information that we generated had physical sense, so that we didn't train any model blindly, basically. So the idea again was to train these data-driven models, different data-driven models, just based on the parameterization. So the model has no physical knowledge. It only has, in this case, the vertices locations, so X and Y coordinates and separation between the fins to predict physical quantities. And that was something novel at the point as well, because usually some models rely on physical quantities to predict, for example, heat flux. In this case, it has basically no information about any physical surroundings. So only using the vertices, we were capable of predicting, again, several thermal performance quantities and some quantities regarding the pressure drop. We measured the accuracy of different data-driven models using different metrics. In this case, mean absolute percentage error and also the mean square error. So here you have some initial results of models that were trained. In this case, it was a neural network and random forest, using the entire of the database. First of all, again, that's why I mentioned at the beginning, we noticed that there were those cases that are highlighted at the bottom that had this opposite basically behavior and only represented less than 1% of our database. So basically, instead of being useful for the model to predict the heat transfer, it did the opposite. It just complicated the learning because there were a few hundred fins that weren't doing what they were supposed to do. So for here, you have some results for the relative error and the relative errors, both for the random forest and the neural network. For example, the neural network is the one that showed the better result, had a relative error up to 10% for predicting the heat flux. So we thought we could do better, basically, but this was the starting point. And then we did the same thing, but for measuring the fluid dynamic performance of these microfins. And basically, in this case, we didn't have fins that basically were outside of the main sphere or space of knowledge. So they performed, the neural network especially performed really well. So we were capable of predicting the total drag, for example, with an error lower than 2%. That's really great, considering that you have no information of physical quantities around in just vertex coordinates. So starting from this, we were trying to think ways of identifying which fins were causing the data-driven model not to learn so efficiently. And in order to do so, we follow like this loop that we call the neural network training strategy. But basically what it is starting from all of the information that we had in our database, we trained two different networks, one focusing on heat flow and another one focused on the prediction, the fanning friction coefficient. which is basically a dimensional way of measuring the pressure drop or the fluid dynamic performance of the microsurface texture. And we train a model and identified which fins had a higher relative error. Because what we noticed is that there were fins that were very easy to predict, let's say it that way, and fins that were really hard to predict. So basically what we were trying to do is flag these fins that were hard to predict by the model, put them aside, reconstruct the database without those fins that were special, let's say, and retrain the model. So by doing so, we improved a lot the accuracy of the model. Basically, the data-driven model was able to focus in on the important information. So here what you have is in gray is the raw data, and then in blue, you have a first loop of the filtering, which means that you train the model, you predict, then you eliminate from the database those things that were shown to be complicated, then retrain again. And by doing this twice, we were capable of diminishing the relative error of the model. In this case, you can see it here. They were from the 16,000 samples that we had, 4,000 things were considered to be outliers. So we put them basically aside. And here you can clearly see the effect that it had on the error. So on the first graphs that you can see here was you can see the absolute error in the heat flux and fanning friction prediction for the model that was trained with the entirety of the database. Now, after one filter, so after putting aside these things that were outliers, we were capable of reducing basically the relative error, and the model was pretty consistent. So this was a good idea, basically trying to move towards having a more robust model that could be implemented in any optimizer. Because again, if you have a data-driven model that is not well trained and you put it inside of an optimizer, whatever results it's giving you probably is not trustworthy. So that's why we focus a little on having a better trained model. So from these first results, basically, we proved that it was possible to construct a data-driven model only trained basically on geometric quantities to predict physical variables such as heat flux and fanning friction coefficient that at the time had not been before. Also, we showed how it's important basically to have a very robust sampling strategy when you're trying to construct your database for training, and we were capable of showing a model training strategy that enabled the flagging of samples that were supposed to be not used for training. So knowing all of this, we will move towards the second part of the research, which was implementing these models that were already accordingly trained inside of an optimizer. So the new idea here was trying to see if there was anywhere outside of our original search space that had things that outperform what we had already known. Now, our space was pretty dense as it was, but again, we generated them randomly. So there was a chance that there was something outside that we didn't see before. So in order to do that, basically we tried this approach of using a genetic algorithm, and instead of the genetic algorithm relying on a numerical solver to run the simulation of the microsurface texture, it's relying on the results from the data-driven model. So we saved a lot of time. And this was something that couldn't have been done before because, again, it was very time-consuming. So the idea, again, was using a genetic algorithm, and in order to be fair, we posed the same constraints that we had when we generated the database. So basically the size constraints and all of these sanity check or feasibility assessment measurements that we included at the beginning, just to make sure that the genetic algorithm had the same restrictions as we had at the beginning when we tried to generate our database. So here you have how we basically thought about the problem. So what we are trying to do is maximize this quantity that is called the performance evaluation criteria. I'm not sure if you're so familiar with it, but basically it's a ratio between the J factor and the fanning friction factor, which are two adimensional ways of measuring the heat transfer efficiency and the fluid dynamics performance of a microsurface texture. And that's what we set as the objective for our optimization. Now, you might be thinking, why use this and not use a genetic algorithm with two targets, basically? Because at the beginning, we didn't know which target was more important. Is it more important to optimize the heat transfer, or is it more important to focus on the pressure drop? So this was a measure that it was widely used in the research, in the literature, as an objective for optimization tasks. Now here you can see on the plot, basically all of the dots that you can see in gray is our database. And you can see in the y-axis is the J factor, and the x-axis is the fanning friction factor. So all of the radial lines, basically, they represent the performance evaluation criteria. So basically, you want to move up these lines to find better results. Now, what's the problem with any optimizer? That in this case, this genetic algorithm was very stubborn. So if you're trying to increase the heat transfer capabilities of a microsurface texture and you include the separation between the fins as a target to optimize, the optimizer is really smart. So it's going to place fins together and say, now you have more surface, so the heat transfer is going to increase. That's true, but that's not what we wanted, basically. So what we found at the beginning is like if we included all of the database inside of the optimizer and we left the separation between the fins as a parameter that could be optimized, then the result was always put fins together, and nothing regarding the contour of the fin, which was the main purpose of this entire investigation. So basically what we did was to divide our database in 5 families, depending on the separation of the fins. And instead of using the separation as a parameter that could be optimized by the genetic algorithm, we left it outside. So the genetic algorithm will focus on optimizing the contour itself. So here, what you can see in different colors are the 5 different families. So UHD stands for ultra high density, as far as the orange one, that it's ultra low density. Ultra low density means fins that are far apart. Ultra high density, it's you have more fins in a smaller space. And instead of running only one genetic optimization or genetic algorithm for the entire optimization, we run 5 different ones for the 5 different families. And by doing so, we compare the results with the brute force approach that we did at the beginning. What do I mean by that? So all of this was basically to compare, okay, could we do it better, basically? We had this brute force approach. We found the optimum with these Pareto fronts, but what about the genetic optimization? Is it fair? Does it do a good job, basically? So what we did also to make sure that the genetic algorithm was giving options of candidate microfilms that had sense, after the genetic algorithm said, okay, this microfilm could work really well, we ran a numerical simulation of that microfilm to make sure that the prediction of the performance evaluation criteria was in accordance with the neural network or the data-driven model prediction, just to make sure that it wasn't having any errors in between. So by doing so, here you can see the results that we got. So the different colors, as I mentioned, want the different separation of the things. And then you have the circles for the database, and then the diamonds, it's the optimizer result. So for example, here you have the results from the ultra low density microfilms, so the ones that were farther apart. And basically what you can see is the optimizer found a better fin. That's the main thing. And the same for all of them. So basically by implementing the data-driven model in a really efficient way, comparing to plugging a numerical solver inside of the optimizer, we found better fins with, again, physical sense for all of the families. And also we compare this with our starting point. So we have this database, we know the optima in the database, we know the optima inside of our optimizer, but how do they compare to a basic regular fins? Is this any better? Like, is all of this work make any sense? So we compare the performance of these fins with both a rectangular shape and a T shape, which was the starting point of our parameterization. So here you can see the result for the heat flux. And as you can see in the square is a rectangular fin, and then the T shape is the diamond. So we outperform both with our database, but more interesting enough with our genetic algorithm, the performance of these fins. And then for the fanning friction coefficient, of course, our fins have a higher fanning friction coefficient, but that's because it's a more complex shape. So it's not as simple as a rectangular shape. So it motivates the creation of secondary flows that promote heat transfer, but also increase the pressure drop as well. And here are some of the samples of the fins that we found to be in the best ones of the optima. Now, before anyone asks, yes, they're weird, but the idea was to learn about the parameterization. So there's no way this can be manufactured as they are, of course, but it's interesting to know how new fins were generated, just starting from this T shape that we started with. So here you can see in pink, so at the left, you can see the optima from the database, and then in blue are all of the optima generated by the genetic algorithm. Now, it's pretty interesting to see, for example, here for the ultra low density, so the ones that are more further away, how, for example, the optimizer went towards finding fins that had like an arrow shape. That motivates the creation of secondary floats, improves the heat transfer in sections where probably if you have a square fin, the flow is just gonna go on top of the fins instead of getting in the gaps in between, which promotes heat transfer. That's very interesting that the genetic algorithm found that. And also here you can see the improvement from the optimizer compared to the database. So basically we improved the performance evaluation criteria for all of the families, which was good news basically, because that means that this is a good way to move forward and to find an optimum inside of our database. So again, these are some intermediate results of what we achieved with this part of the investigation. Basically, we were able to construct a robust optimization that didn't only focus on the separation of the fins as a way to improve heat transfer, but also focused on the contour of the microfins. Also, we were capable of creating unrestricted fin shapes, which means that these are new fins that have never been used in industry before, focusing both on macro and micro characteristics, defining these performance evaluation criteria as the main focus of our work. And we were capable of improving the performance evaluation criteria between 0.08 and 0.28 units for all of the families. So we found better alternatives that we had already done in the start of our brute force approach. So this was a better way, like it was supposed to be, to do a guided optimization to find optima for microfin shapes. So after we finished this part, basically we landed on the idea of like, okay, we have found fins that outperform the ones that we did with our brute force approach. But all of this work was mainly based on coordinates around the microfin, and we could do better. The main problem of this is that we had 15 parameters that we needed to focus on. So X and Y coordinates around the microfin shape. So we wanted to investigate new possible ways to parameterize this geometry and avoid the data-driven model to memorize information, because at the beginning, or as I've mentioned, we had a lot of geometries to learn from. But a common question could be, do we need all of them? Like we had 16,000 geometries, but probably not all of them would have been necessary. Could we optimize basically the amount of information that is needed for any data-driven model? So then you can move towards to, okay, so if I know that with 100 fins is enough for the data-driven model to give a good prediction, maybe I can move towards running high fidelity simulations of less fins and having a more accurate result of the performance of such fin. So here it's where we landed on this idea of using elliptic Fourier analysis to parameterize a geometry. Here you have an example of a reconstruction of one of the fins that we have in your database based on this elliptic Fourier analysis. So this is a very compact and smooth representation of parameterization and geometry, and probably it's not the first thing that you would think of because we have really sharp edges. But now the question would be, is it necessary to define these sharp edges so precisely to predict integral values such as heat flux and pressure drop? So that's why we consider using this approach. So the idea was to measure the Fourier descriptors, which is basically you construct a complex contour and basically get the magnitude and the phase by applying the Fourier transform to the contour. And the idea is like the first Fourier descriptor is gonna hold the most general aspects of the geometry. So this Fourier descriptor only holds basically how big the fin is and how tilted it is, like to one side or the other. And as you move towards adding more and more ellipses, so more and more Fourier descriptors to your contour, you capture high frequency details. So probably if you want to capture this pointy edge in the fin, then you have to add up to 10 Fourier descriptors. But if you only want to capture the overall shape, maybe with 3 Fourier descriptors is more than enough. So as I've mentioned, what you have to do is to apply the discrete Fourier transform to the complex representation of the contour. And basically what you have is the first Fourier descriptor is gonna capture the center of mass, and then whatever you add is gonna be adding more detail to it. So for example, here, what you have for the first elliptic Fourier descriptor is basically 2 counter-rotating circles that construct an ellipse. The first ellipse just holds basically the magnitude of the fin, how tilted it is at the beginning, and then whatever you add on top of that is gonna deform the first ellipse to capture or to be closer to the reconstruction of the complex contour. So now that we had this idea, the next question was, okay, so we know that this could be an option to parameterize of geometry, but how much information or how many Fourier descriptors do we need to correctly define a geometry? So in order to do that, the first thing that we did was basically measure the reconstruction error. So using from 1 up to, in this case, 15 or 14 Fourier descriptors, we reconstructed the contour and measured the error, the reconstruction error of the contour. And basically you can see that you hit a plateau. What does this mean? That there's one point that it doesn't matter how many high frequency details you want to add, the reconstruction error is fairly the same. So it's not useful basically to use more input variables for your data-driven model, for example, because the information that it's being added is not useful to identify or parameterize the contour. So for example, in this case, we chose 4 Fourier descriptors as the elbow, basically of the curve of the reconstruction error. And before moving forward, we did some inverse design approach. Basically, we reconstructed all of the contours using 1 up to 4 elliptic Fourier descriptors, and we tried to find the correct match inside of our database. What does this mean? So you reconstruct a fin with 1 Fourier descriptor, and then you try to, with this reconstruction, find the correct fin in the database. If you're not able to find the correct one, that means that more than one fin has the same first elliptic Fourier descriptor. So that's not a unique way of defining this contour. So in this case, here you have the result for 1, 2, 3, and 4 Fourier descriptors. By reconstructing the complex contour using 4 Fourier descriptors, we were capable of finding all of the correct matches in our database. Now, this is specific for our case. So you would have to repeat this for any other application. But for our case, with 4 Fourier descriptors, basically we're capable of finding all of the correct matches in our database. So we moved towards training a model only using 4 Fourier descriptors instead of using the 15 vertices around the contour, which was kind of not a good way of defining the contour. And to move towards the measuring, basically the effect of these elliptic Fourier descriptors, first we tried, and this is something that we did also at the beginning, and it's kind of common sense. Let's try to find a latent space that of basically of combining these 15 parameters that I have and see if I can represent in a more efficient way the original search space, and the answer is no. For example, here 2 really basic examples, but this is principal component analysis based on the 15 fins, and then the elliptic Fourier descriptors. And basically there's no combination of principal components that will simplify or reduce the number of inputs that you will need to train a data-driven model. So even though this is a way that in some cases it works, since we are working with a highly irregular in complex high dimensional space, techniques like these ones don't work to find latent search spaces. That's what motivates another, the use of, for example, elliptic Fourier descriptors that are really maybe a more complex way of finding this latent search space. And also, in order to evaluate the accuracy of the models, we were trying to define an interpolation and extrapolation dataset inside of our space. Now, this is a problem because it's really hard to define a set of fins that have these 15 parameters really different from another set of fins. It's really compact. So it's it doesn't matter how you select them, there's gonna be some coexistence at some point. So probably the model has seen that value at some point before, because it's impossible basically to build a fin outside of the minimum and maximum requirements of size that we set at the beginning. So in order to be as fair as we could, basically we calculated the centroid of original data space, and we measured the Euclidean distance of all of the samples in our database to the centroid, and we chose basically the 20% that was farther away as our withheld data set, just to see if the models were memorizing or if they were extrapolating good enough. Here you can see what I meant by the idea of that is really difficult to find a set of things that are kind of different from one another. So here you have the representation of this training data set, which are the things that are closer to the center of the search space. And then in blue, you have the 20% that are farther away. And even though they're farther away from the center of the space, there's still some coexistence. So of course, some of the things that are kept for this validation step have input parameters that were seen for training, because there's no way that that wouldn't happen in this case. So following this training and withheld data sets, basically we compared how well the elliptic Fourier descriptors will hold against the Cartesian mapping description. And this was pretty interesting because we measured two things at once. First, if the elliptic Fourier descriptors outperformed the Cartesian mapping, and then how much information were they needing for training, basically. So what's the result here? I wanted you to focus on the right of the plot because those models were trained only using 1% of the data. So a really, really small quantity. And as you can see there, the 10 points that you can see in the x-axis were different trainings of the model. And as you can see, the Cartesian mapping is not very robust and also was really dependent on which fins were included in the training dataset, which is also a question that you might be thinking about that I'll go afterwards. Whereas the elliptic Fourier descriptors weren't so dependent on the amount of information that you give them for training, and only using 1% of the database, it wasn't enough basically for the model to train well enough and being more robust than the Cartesian mapping. Here you can see an overview from a more general point of view, because here you have an x-axis using 1% of the data for training up to all of the data for training. And this is really interesting because with smaller data sizes, so these two sections over here, the red sections, what you can see is that the elliptic Fourier descriptors have a lower error, lower dispersion, and almost with smaller data sizes, you can, from 10 to 20% of the data, even less, you can have as good as a prediction as using the entire database. What this is telling us is that it wasn't necessary to run 16,000 cases, but we didn't know it 4 years ago, but good thing to know now, basically. And also, as I've mentioned, the Fourier descriptors show a better accuracy for limited data. So focusing on reduced data sets, which is what everyone is interested about because it's cheaper to run less numerical simulations, we basically evaluated more in detail the training and validation error versus the withheld dataset, which was this extrapolation dataset, to measure if the model that was trained on the elliptic Fourier descriptors had a better capacity to generalize. And as you can see, it has a better capacity to generalize. So if you train only, for example, there you have training only on 1% of the data, the extrapolation error is lower with elliptic Fourier descriptors than with the Cartesian mapping. And also here, you can see really clearly. So training with 0.5 up to 20% of the database, you can see that for the Fourier descriptors, there's one point that it doesn't matter how many samples you include. Only 1% is almost enough for the error to be as low as having 20% of the database. Now, for the Cartesian mapping, it's not the same thing. So you can see that if you add more information, there's a greater effect on the relative error, which means that it's not the best way, basically, to describe the geometry. And the last question that we asked in this part was what I mentioned before. Okay, so we already know that the Fourier descriptors work kind of well with reduced datasets, but how does the construction and the composition of the training dataset, so basically which fins do you include in the training dataset, have an effect on the training? So since our data space is very compact, it's really hard to find clusters or any fins that outperform for any reason other ones. So we followed some basically methodology that was used in literature for other purposes. So we train a model with the entire database for a little amount of epochs. And based on the relative error, we separated the fins into easy, intermediate, and hard, meaning fins that were easy to predict, so they have a lower error with a model that it's not trained all the way, and then fins that are hard to predict. So basically the data-driven model needs to think a little harder to predict those ones, and whatever is in the middle. So these are just terciles. And we constructed what we call this composition matrix. So we did all of the combinations possible, basically, of different percentage of easy, intermediate, and hard fins. And we did that to evaluate the relative error for training and withheld datasets as well of these models to evaluate if the percentage of any of these classes had an effect on the error of the model. And in order to be able to visualize this, we used ternary plots, which I don't know if you're familiar about this, but basically what it's represented here are the different combinations of the 3% of data. So for example, for the point that is highlighted there, there is that's a training data set that has 40% of easy fins, 40% of hard fins, 20% of intermediate fins. And what we did was populate the entire ternary plot to see if there was any pattern that you could see. Basically, if, for example, the fins that are, or the training data sets that are at the point, basically, of the ternary plot, those ones have a higher percentage of harder fins. So we wanted to check if, for example, those fins had a higher error, or if the color was kind of consistent towards the entire ternary plot. And here you can see the results. So it's important to point out that these plots have an absolute color map, just for you to be able to compare the different ternary plots. So each row has a different percentage of data used for training. So starting with this one that has only 0.5% of data for training up to 20%, we kind of see a lot of things here. One of it, it's basically the idea that if you have enough information, it doesn't matter how you construct the training data set for this case. So if you use 10, 20% of the data, you can put whatever you want, basically, in your training data set, that the model is going to perform fairly well. Now, if you have less information for reduced data set, you can see that there's a pattern there. So colors that are closer to yellow means that they have a higher error. And as you can see, this yellow color is usually towards the top of the ternary plot. This means that the training data sets that had a higher percentage of hard fins in them had a higher error. And here with a local color map, so basically each ternary plot is plotted with its own local color scale, you can see patterns in each of the ternary plots. So from an absolute point of view, you can already see there's something in relation with how you construct your data set has an effect on the training and withheld errors. And here you can see really clearly. So for all of the percentage, but more so for those fins that are included in the smaller data sets, if you include more harder fins inside of your data set, then the model is not gonna perform as well. Also, it's important to, for us, it was important to plot both the training and the withheld data set to basically show that the model was not overfitted, so that it didn't have a lower error for the training data set. And as you can see here, for example, doing a little zoom because it's a lot of information. Again, you can see that the fins that have a high, the training data sets that have a higher content in those hard fins show a higher error than those that have a higher percentage of easy fins that have the lowest error, so the light blue. And if we want to look at this from a C3 point of view, here the height of the plot, it's a comparison of the relative error of each dot compared to a model that's trained with 100% of the dataset. So basically, whatever surface is close to the one means that that's a model that has an error close to a model that was trained with the entire dataset. So here what you have are different surfaces for the different percentage. So this is a model that was trained only with 0.5% of the information, 1, 5, 10, and 20. And here you can see really clearly that the elliptic Fourier descriptors show a lower error compared to the Cartesian mapping for the smaller datasets. Because here you can see that with 0.5 and 1, the relative error compared to a model trained with all of the information, it's higher than when you describe the geometry with elliptic Fourier descriptors. Now, the same idea appears again. If you have enough information, it doesn't matter how you do it, the error is gonna be good. But the thing is that you wanna save as much time and resources as possible. So if you want to run fewer high fidelity simulations, elliptic Fourier descriptors are a better way to parameterize your geometry in order to predict, in this case, the performance evaluation criteria. So here, as an overview of this last step of the research, basically we show the efficiency of the elliptic Fourier descriptors for describing complex irregular geometries. We also define this new heuristic way of defining a classification metric in order to measure the impact of the composition accuracy on the fins. Basically, we show that it has a higher effect, the composition of the training data set, when you don't have enough information, so for reduced data sets. Also, that there's a relationship, as I mentioned, between the composition of the data set and how big it is your training sample. And also we show that with elliptic Fourier descriptors, also with 1 to 5% of the data of our entire database is good enough to have a model that it has or that shows as good as of an error of a model that's trained with the entire database. And these are some general conclusions of the overview of this research. So basically, we've proved the potential of using artificial intelligence for a complex mathematical problem as parameterization in these complex shapes. Also for a real application of an engineering problem that it's complex. And we constructed our in-house database that it's basically a good proof of concept case to start with. We build surrogate models that are robust enough to be implemented in a robust optimization problem. We founded new unrestricted microfilm shapes for design and to learn from, to design new microfilm geometries, and we propose this new parameterization tool, the elliptic Fourier descriptors, to improve the parameterization that we started with the Cartesian mapping. And with all of this, thank you very much. And if you have any questions, I'll be glad to answer.
Thanks for the nice talk. It was very interesting. I was wondering, so say if I wanted to create a new database, how would I know when I've collected enough data? Like, because here you analyze the database that was already created, but if I'm creating a new one.
So for this case, basically what we should have done at the beginning was backwards. Instead of constructing the database and then starting from smaller and building up, I would suggest starting from smaller quantities of data, then testing the model and building smaller by smaller quantities and comparing to what you have before. And at some point, you're gonna hit a plateau. So don't run thousands of simulations without looking at them. It's better to run smaller quantities, train a model, and then compare to the rest. There's gonna be one point where you don't really see an improvement. So that's where I would say stop. But this is very context dependent. So it depends on the problem. So in this case, as I've mentioned, the percentage and stuff that I was mentioning, it was for this microfilm case, but other cases might be more difficult to determine.
Could you run back to section 3?
So this part?
Yeah, and specifically the plot where you're showing the, this one, yeah. So here you have, you've decided on some fin shape based on this genetic algorithm, and now you plug that fin shape back into CFD and generate the results here. But you could also just look at what the trained neural network that you had to use the genetic algorithm, what those results would be. What was the mismatch between what the CFD found the performance of the fin shape was versus what the neural network found or what the neural network thought the performance of the fin shapes should be? Does that make sense?
Yeah, so why was the result of the neural network and the CFD not the same for some of them?
Yeah, so for the final fin shapes that you decide, I would guess that the neural network would be optimistic or over optimistic about the overall performance. Was that the case?
Yeah, so the fins that we chose as the optima were at the beginning were not the best ones set by the algorithm, because the genetic algorithm that was trusting the neural networks did said that some fins had a really good performance, but it was a mistake. So that's why we had to do the last step of, okay, if we really think that these are the optima and they make sense, let's double check, run the numerical simulation and make sure that the result matches. Now, the neural networks that were implemented inside of the surrogate model were not perfect. So it's expected that for some fins, it can have some trouble. And some of the fins, I mean, the shapes are really special. So there's a lot of phenomena that have to be taken into consideration. Also, these are run simulations, so it's not the best starting point, let's say. So we didn't do it, but I would suggest if I were to do this again, with the optima, run, for example, some less simulations and just double check that what you're seeing as optima is the real optima. Now, the good thing of using the data-driven model inside of the optimizer is that we've kind of be putting in the line towards the optima in a faster way than just running the numerical simulations, because that's really costly. So that's why we chose this upload. But I would say that, and that's what we did, always double check that the neural network is predicting something that is trustworthy, basically.
I have a question. It's actually related to the mismatch. So this is based on like a CFD model, but if you actually build these fins, I'm guessing you get like slightly different heat transfer coefficients and pressure drops. But those would be much more expensive to actually 3D print and test those. So I'm curious if you had, the ability to make thousands of CFD points and maybe a few dozen, you could fabricate a few dozen of these things. How would you mix those types of data and experiments to like improve the results?
So first, if I were to do it at the beginning, I would use adaptive sampling to kind of guide like which parts of your search space are more useful to be running, for example, expensive simulations to improve the accuracy of your results. Now, if I would have the ability to build any of these fins, I will do so with the fins that are the optima, just to triple check. So basically I have the optima with my genetic algorithm, I double check with my numerical solver, then I print them and I see if there's like a correspondence in between. Also, for this specific case, it will be good to have one within each family. So don't manufacture 5 or 10 fins that are basically inside of the same family or very similar. Just manufacture those, both the ones that show really good performance and the ones that are very challenging or that have like really uncommon shapes, just to see how they do. That's how I will approach the problem again. And again, just trying to do some more thoughtful of like, if I have the ability to run more expensive numerical simulations, place them in places in my search space where the uncertainty of the model is higher. I would say that. Yep.
There is a question in the chat.
Oh.
Doris is wondering if you thought of some sort of dimensionality reduction of your first coordinate-based bin data set to get a different basis that you can use for generating bins. I know you show some failure mode for PCA, but not sure about other methods.
So we tried different methods, and also I've showed PCA because it was the simplest, let's say, that I could show. We tried different manifold learning approaches to find a different reconstruction of my initial data space, but we didn't find a method, not PCA nor on other thing, basically, that outperformed the beginning. So we, for example, you can use PC8 and you landed on having to use 10 principal components to define your original search space, but that's not really saving up on degrees of freedom because you still have 10 inputs that you have to use for your model. So yes, we tried different techniques, but basically none of them showed like outstanding results. The best one was trying to redefine it with the elliptic Fourier approach.